Okay, let's go ahead and get started. I'm Charlie Smith, the Executive Director of ESIG. I want to welcome you to our ESIG monthly webinar for November and give you a little bit of background on ESIG. For those of you not familiar with ESIG, we're a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of the energy transition. We do this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resource materials. I also serve in a leadership role with the Global Power System Transformation Consortium, the GPST, whose mission is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scope and speed. ESIG leads Pillar 1 of the 5 pillars, which deals with the research agenda for the system operators. And I'm very pleased to have a speaker from ERCOT, one of the 6 founding system operators of the GPST, here with us today. More information on the GPST can be found at globalpst.org. We just finished our fall technical workshop and working group meetings, which were held in Minneapolis last week. We had an attendance of 170 persons, which was more than double the attendance at our spring workshop in Tucson. So we feel like we're well on our way to our pre-COVID levels of attendance. And due to the great work of our wind and solar forecasters, we were provided with temperatures in the mid-70s early in the week, which set the stage for a great workshop. Our next workshop will be in March in Tucson, and I've been promised that the temperatures there will be even better. Further information can be found on our website. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on the ESIG website. If you're new to ESIG, I strongly encourage you to follow up with us if you like what you hear, and I think you'll be pleasantly surprised. ESIG membership will give you an opportunity to participate actively in all of our working groups and task forces. You can find us on the web at esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. Okay, just a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we're using the Slido platform. So to ask your questions, please go to slido.com and enter ESIG3 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions to allow you to cast a vote to help prioritize the questions submitted. We plan to save 10 minutes or so for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. So today's topic is going to be the Odessa disturbance events in the Texas Interconnection, having to do with the loss of PV solar plants in West Texas after system faults during the past 2 years. This is becoming a serious problem which needs some serious attention. And here to talk with us about it today is Patrick Gravois with the Operations Analysis Group in ERCOT. Patrick has been at ERCOT since graduation from UT Austin in 2013. After some time in grid applications support, working on control room applications in ERCOT, he moved to the Operations Analysis Group in 2021 with a focus on grid event analysis and operations improvement. Since the Odessa event of 2021, he's become the lead engineer working with Inverter-Based Resources to improve ride-through performance during system disturbances. So I think we have the right guy here to talk with us. Patrick is new to ESIG, and it's my great pleasure to welcome him here today. Today's webinar will give us an update on the Odessa disturbance events in May of 21 and June of 22. These types of events have the potential to increase in magnitude and pose severe reliability risks to the system. This webinar will focus on ERCOT's root cause event analysis process and results, and the collaboration needed between ERCOT, NERC, TRE, the Texas Reliability Entity, inverter manufacturers, and generator owners to identify root causes and implement corrective actions. I greatly value the contributions of ERCOT to ESIG and the industry, and I look forward to what Patrick has to say. Just a short reminder once again to use Slido at slido.com with the event code of ESIG3 to ask your questions. And I want to let you know that Patrick has no video today. He's got a little technical malfunction there, but we'll have his voice with us. Okay, without any further ado, let's go ahead and get started. Patrick, I'll now turn it over to you.
All right, thank you, Charlie. That was a great introduction, so I don't think I need to spend much more time doing any intros for this topic. But like you said, we'll be going over some of these larger events in the Odessa area in Texas, where we had system faults resulting in a large loss of particularly solar farm generation. All right, so we'll start with the first event and kind of do an overview, go through the analysis and some of the things that were done since that event, and then leading into the second event in 2022. So the first event occurred May 9th of 2021 at 11:21 a.m., where there was a single line to ground fault that occurred on a generator step-up transformer at a combined cycle plant in Odessa, Texas, right around Odessa, Texas. It was a normally cleared fault, cleared in about 3 cycles. The combined cycle plant experienced a partial trip and a run back of roughly 200 megawatts. We do have about 200 PMUs sending in real-time data throughout the system across ERCOT, many in West Texas as well. So from those PMUs, we were able to look at some of the voltages that occurred during the fault conditions. We saw low voltages of about 0.7 on 345 kV, 0.84 on the 138, and 0.5 on the 69. We were able to determine pretty quickly that it occurred on the 345 kV system as well. We're able to determine that the voltage that we were seeing from the real-time PMUs were all within the no trip zone of the voltage ride-through requirements in both NERC PRC 24 and ERCOT's own nodal operating guides as well. So right away we were questioning why we had so many resources tripping off due to this normal clearing fault. So we had a non-consequential loss of approximately 1,112 megawatts of solar generation from about 10 different facilities. Now that's just counting the facilities that had at least 10 megawatt loss or more. There were several others that had a smaller loss, but we did not go that deep into it. It kind of had a cutoff in order to get, what we needed accomplished. There were some wind units as well, but we're going to focus on the solar because it was dramatically more than the wind resource losses. The frequency dropped to about 59.82 and recovered in about 3 minutes. This was categorized as a NERC 1I event, which is a non-consequential interruption of inverter type resources aggregated to 500 megawatts or more, not caused by a fault on its own equipment. So this was in some cases, the fault was pretty far away. West Texas is a huge area. We had some units that were tripping off, a couple hundred miles away from the fault. So this is directly from the NERC Odessa Disturbance report that was released last fall on this event. So this is a breakdown of the inverter manufacturers that were involved in this event. So there were 3 primary OEMs that had their inverters trip off during this event. We're going to call them OEM 1, OEM 2, and for these slides, OEM 4. So on the right, this is the solar capacity at ERCOT at the time of this event. You can see OEM 1 had the largest. OEM 2, they made well over 50%, maybe close to 60% of the total capacity of solar in ERCOT. And then OEM 4 was the 4th largest. So, and those 3, OEM 1, 2, and 4, made up 100% of the megawatt losses we saw during this event, with OEM 1 being 63%. We did a lot of root cause analysis. So we sent out RFIs to all the facilities asking for, why the inverters tripped. We got all those responses. We went through, most of them had fault codes that said why the inverter tripped. We did a lot of follow-up work with NERC and Texas ERE to reach out to these facilities and do more root cause analysis. And all of this went into the NERC report that was released as well. So this is the breakdown of the major causes of reduction that we saw. The biggest was the phase lock loop loss of synchronism, 389. Then we had overvoltage, momentary cessation. All of these were things that were typically seen in other events that NERC had already analyzed, like the Blue Cut Fire in California and a couple other events as well. Some of them were kind of, really particular, like a feeder under frequency breaker trip, things of that nature. But here's the breakdown. The biggest was the PLL loss of sync, and the overvoltage made over half of the losses here. So we're going to talk about each of these individually. First is the PLL loss of synchronism. So there were 2 solar facilities that had reductions of 239 megawatts and 150 megawatts. This was one particular OEM. This is OEM 1, also identified in prior events analyzed by NERC. Realize this is a systemic concern with these facilities. So this occurs when there is a voltage phase shift greater than 20 degrees. We were able to talk with the OEM and discover that this function is not really necessary for equipment protection, and it really wasn't needed for the transmission level system. So this was one that we were able to fix relatively easily. The OEM said that they could disable this function upon request from the generator owners. And they are shipping out their new inverters with this function disabled. So over the course of the last year, first we started with the 2 facilities that tripped this function, and they went ahead and disabled this function. And then we reached out to all other facilities with these inverters to ensure that this function was disabled as well. And we were able to accomplish that. Towards the beginning of this year, we were able to confirm all of these had been disabled. The next was the inverter AC overvoltage. This one is a little more complicated to mitigate. There were 2 solar facilities, 205 megawatts, 64 megawatts, the next largest cause of reduction. So what we were seeing is the inverter protection is based on voltage at the inverter terminals. Voltage ride-through requirements are for the POI. We're finding there's a pretty large difference between the POI voltage and the inverter terminal voltage as well. So from those real-time PMUs and PMU data sent in from these facilities, we didn't really see any voltages above 1.1 per unit during this event. But facilities were seeing inverter terminal voltage at 1.25 or 1.3 and tripping themselves off. The OEM, this is one particular OEM as well, for these 2 facilities. They had stated that they cannot relax those. This is those thresholds for the overvoltage. It was needed for equipment protection. So the only corrective action we were able to come up with is reducing the reactive injection. We were seeing that the reactive injection in response to the low voltage due to the fault was sometimes coming in a little late, a little bit too much, and it was causing this high voltage at the inverter terminals and causing these plants to trip themselves off. So this is an issue that was identified on several events. We've been covering it pretty well over these events as well. We did have these facilities start doing some PSCAD modeling to see what would happen if they reduce this K factor, and they did see improvement. Unfortunately, none of this got implemented before the 2022 event. The next cause was also overvoltage, but this was at the feeder level. So this was one facility in particular, kind of the same root cause problem. You had reactive injection coming in a little late and a little bit too much once the fault had recovered and system voltages are recovered. So you're injecting reactive into a high voltage situation, causing high voltage at this point at the feeder breaker level. And so all of their feeder breakers tripped off due to high voltage. So we found out that that was set directly on the PRC curve, directly on 1.2. So the team, NERC, TRE, and ERCOT was asking, hey, why do you have is this feeder level protection even needed? What are you protecting with this protection? They really couldn't answer that question. They couldn't clarify why that was set that way, only that, you know, they saw, hey, there's a 1.2 trip setting, so we probably should trip it there. But that's not the intent of the voltage ride-through curves. It's not a must trip above 1.2. It means you're allowed to trip. So that was something we've really had to stress over the past year. NERC's been stressing this a lot, that just because you go above that 1.2, you go outside those VRT curves, does not mean you have to trip. We prefer that you don't trip, actually. So they were able to disable this feeder level protection. But as we were studying the response from this unit, we realized, hey, just because you disable this feeder level protection, now you might have inverter protection that could trip off. You're still seeing this high voltage in your plant. So we continue to work with this facility over the past year. They did have some mitigation that they were putting into place. But again, that did not get put into place before the 2022 event. So we'll come back to this facility as well. The next is a single facility that had momentary cessation. So this is probably the oldest solar facility, transmission level solar facility in ERCOT. This was circa 2015. It came online 2016, but the design was more 2014, 2015. So they have legacy inverters, and it was thought that they really could not disable the momentary cessation, and that was set to go anytime voltage is below 0.9 per unit. They would go into momentary cessation, which means it would current block for all reactive and active power. So this doesn't really meet the requirements, because you're required to provide reactive during the low voltage conditions. So again, this being an older plant, I think it just really wasn't looked at closely when this plant was being commissioned. So what we did with this plant, even with the momentary cessation, we would expect them to be able to come back and recover to their pre-disturbance output within under a second, really. And that's not what we saw from this plant. We saw this was 2 units in one facility. One of them, it took about, you see the ramp rates in the top right. One of the units took about 1.5 minutes to come back. The other took closer to 5 minutes. So they really couldn't explain why these 2 units took different time periods to come back. They thought they were set to the same ramp rates. So they had a lot to look at from this event, but it was clear that they weren't meeting the recommended performance from the NERC reliability guidelines. Since the 2021, this plant had replaced their entire plant level controller, retuned the logic, and they were expecting to be able to come back quickly after momentary cessation, but we found that was also not the case in the 2022 event. And again, we'll come back to this facility later. The next is under frequency. So this is kind of a big topic as well. There was both inverter level under frequency and feeder level under frequency. For the inverter level, we had one facility that had all their inverters trip on a grid under frequency below 58.2. The lowest grid frequency was actually 59.82. So this, I think, was basically just the wrong settings. So it took a while for them to get this set correctly. We also had a feeder breaker trip due to under frequency, and this was low 57.5. So this is something we've really been trying to work on in the industry as a whole. So on the bottom left, we've got PMU data from out west. So you see the fault occurs, we have this sharp decline in frequency during the fault conditions, then it returns, and then it starts to drop due to the loss of generation on the system. So frequency ride through is really meant for the grid frequency due to this loss of generation. It really shouldn't be tripping off during this fault conditions, because you're trying to read a frequency in a matter of 100 to 200 milliseconds. So you really need to measure frequency over at least a 5-cycle window. But a lot of the way the requirements are written, they say, hey, if frequency goes below 57.5, you can trip immediately. And that's what they're doing. They're setting no time delay. So some of these devices, both inverters and breakers, are having this reading of below 57.5 hertz and tripping automatically. So we're really trying to eliminate this completely from the system. And this is something the industry needs to address. NERC has changed some of their standards, and they're going to continue to modify the standards to really get this point across to not be tripping due to frequency during these fault conditions. So both of these facilities, had issues again in 2022. So we'll come back to this as well. The rest, we had some unknown issues. We had some older inverters that had a OEM that is now out of business. So it was very difficult to find who took over the service contracts and what we could do to improve the logging capabilities. They also had lack of PMU data or high resolution relay data. So we're really unable to determine the root cause of these reductions. So it was 2 facilities that were unknown. And then we had, a aggregate of a bunch of smaller facilities that were not analyzed because they didn't meet that 10 megawatt threshold requirement. So we'll come back to this as well in the 2022 event. All right, so let's move over to the 2022 event in June. That was around 1 p.m. Another single line to ground fault occurred at the same substation due to a lightning arrestor failure right near the Odessa area. Fault again cleared within 3 cycles, consequentially tripping off 542 megawatts of thermal generation at that site, at that one combined cycle plant. We also had an additional 309 megawatts lost from a combined cycle plant all the way in South Texas. So we had to follow up with them. That was clearly some misoperations that they had at that station. They should not have tripped for a fault in West Texas. But we're not going to spend too much time on the thermal. We're focusing on the solar here. For this event, we had a non-consequential loss of about 1,710 megawatts of solar. So we had a nearly 50% increase in the loss of solar from roughly identical events that were 13 months apart. We knew this was a concern. Solar growth in Texas has been huge over the past couple of years. It's been close to doubling every year for the past 3 or 4 years. And we still have about 20,000 megawatts in the queue right now. So we knew that this could have the potential to have larger events if this wasn't addressed. So this event was really a wake-up call to us that, we really had to get these mitigation plans into place as quickly as possible. So we were able to move a little quicker for this event. So we had a combined loss of 2,560 megawatts of generation. And then we had 1,100 megawatts of load resources that were automatically deployed to provide that responsive reserve. So although the frequency dropped to 59.7 hertz during this event, by deploying the load resources, the frequency recovered in 80 seconds due to those load resources. This one was categorized as a NERC Cat 3A event, generation loss greater than 2,000 megawatts. So for this event, I've got some screenshots of some of our PMU data. So this is the real-time PMU data from West Texas. You can see there were 2 clear faults, the fault and then a reclose about 10 seconds later. The lowest voltage recorded out west was about 0.7 per unit from a PMU right near the fault on the 345 kV. The 138 kV, we saw the highest voltage of 1.1, but again, all of this was well within that no tripping zone that we have in our nodal operating guide requirement, section 2.9.1. There's a screenshot of that below. And again, the fault cleared normally within 3 cycles. Now we have frequency of the real-time PMUs. Again, you're seeing this sharp drop in local frequency. So this is just a couple of PMUs across the system that are seeing this, measuring this quick low frequency. Again, you shouldn't have anything tripping in this period right here. And then we have the frequency due to loss of generation get down to about 59.7. A couple PMUs got a little lower, but for the most part, 59.7 was the lowest, and it recovered pretty quickly. And then you had the reclose event as well. So this is a screenshot from our nodal operating guides. This is kind of what I'm talking about, the 57.5 hertz or below. The way this is written, people seem to be taking this very literally and not providing any kind of delay to measure the frequency properly. So they're having this frequency, 57.5 that they see for one measurement for, 2 cycles, and then they trip. We didn't see anything for the over frequency, but you can see it's kind of there as well. Here's a map of the 2022 event. This was 14 different solar facilities with a loss of 10 megawatts or more, up from 10 from the previous event. Again, the 1710 megawatt loss, up roughly a little less than 50%. So I want to be clear, we're not including generation that reduced megawatts and came back immediately after low voltage ride through, because that's allowed. We expect these units to drop some megawatts proportional to voltage. The voltage is dropping, so of course the megawatt output is going to drop as well. And they're also trying to provide reactive during this fault condition. So for facilities that reduced their megawatt and came back within, half a second or so, they're not included in this aggregate megawatt loss. But 8 of these 14 facilities were a lost generation in the 2021 event as well. So only 2 of those 10 were not from 2021 did not repeat again for this event. But here's your map. Fault location, same location, kind of a somewhat smaller area. We don't have that one way up in the panhandle. That was due to the PLL loss of synchronism that was disabled. So they were one of the ones that that rode through the second event, but were involved in the first. So the remaining 6 of those 14, in 2021, they were either in commissioning, they were able to ride through the event, or their megawatt loss was insignificant. All right, so here looking at the inverter type per megawatt loss and the total capacity again. So on the left, we've got that same pie chart that showed you previously from the 2021 event, the same 3 OEMs, and then from the Odessa 22 event, still the same 3 OEMs, pretty much the same proportions as well. OEM 3 is the one that's out of business, so their proportion kind of dropped a little bit, and it will continue to shrink. It shrunk in the total capacity as well, but we're still seeing OEM 1 and OEM 2 make up over 50% of the total solar capacity in ERCOT. We've got a few others that are coming along as well, but this is a good idea of the makeup of where the issues are. All right, and here are, again, we went through the RFI analysis, we went through follow-up calls with all facilities, looking at the root cause analysis, and this is the results of all that work. So we're seeing kind of a different set of root cause. The largest test this time was AC overcurrent, which is something we didn't see in the 2021 event. Volt phase jump is a new one as well. This is similar to the PLL. We disabled the PLL loss of sync. Now we're seeing the volt phase jump instead. Over voltage is still there, and we've got a couple other ones. The VDC bus balance is a new one. Bus imbalance is a new one, and then we've got 2 of the other facilities as well. So again, we'll kind of go through these one by one. Overcurrent. So we had 3 facilities lose a combined 445 megawatts. On the top, what we're seeing here is you're seeing a distorted voltage waveform. This is at the inverter level. You see this phase shift can cause a spike in the current. So this is something we saw in 2 facilities that had all their inverters trip off. Both of these plants were not involved in 2021. They were still being commissioned. There are 2 different levels. There's a minor 140% of rated current, or a high 150%. And this just, the lower fault allows them to come back online more quickly. You know, after a few seconds, the high takes about 5 minutes for them to come back on and reset. So this protection cannot be increased or disabled. This is designed to protect the IGBTs within the inverter that can be blown with high current. So you cannot increase this protection. But what the OEM was able to do was develop, and they're currently testing a software upgrade that can prevent the overcurrent from happening in the first place during these voltage disturbances. Basically, it's not momentary cessation, but it's basically doing a little bit, it's changing their pulsing, pulse width modulation just a bit to reduce those overcurrents happening. Like I said, they're still testing. They're hoping to get this finished testing and get this deployed throughout the fleet before the end of the year, but we're still waiting on that testing to be finished. We had one other plant with the OEM 3 inverters that only had about 10% of its inverters trip, 10 megawatt loss. Again, this is the one that's out of business, so we've had difficult times getting some corrective actions for this one, for this plant. The next is a volt phase jump. So this is an anti-islanding protection, primarily used in distribution. It is not needed for the transmission level, but it is required for the UL 1741 certification. So that's why it goes shipped out with this protection in place. So this was 3 plants that had all the inverters trip on this fault code for 385 megawatts. The OEM has confirmed it's not needed for inverter protection. So they've recommended that you can either disable the protection altogether or extend the threshold. Right now it's set at 15 degrees. They can extend that out to the max of 35 degrees. The OEM verified in some simulations that if it was set at 35, this function would not have tripped for this event. But it's up to the GO to choose if they want to extend the threshold or disable it altogether, and they need to authorize the OEM to do that work. So out of the 3 plants, 2 of them have already, one is extended the threshold, one is disabled, and the 3rd plant will be extending that threshold within the next month. Out of these 3 plants, 2 of the plants tripped on AC overvoltage last year. Had not mitigated that. They were in the process of mitigating that still, but then they tripped on a different root cause this year. And again, one of those was a PLL loss of synchronism that disabled, and this time they tripped on the volt phase jump instead. So kind of a similar root cause here. AC overvoltage, seeing this one again, kind of typical. This facility, this is the one that had its feeder breakers trip on under frequency last year. They disabled that, and now they were tripping on overvoltage. So we're seeing this, you know, they're fixing the original thing from 2021, but now they're having a different thing trip them off in 2022. This is, again, we saw voltage at the POI only get to 1.06, but we had terminal voltage reaching above 1.3 per unit. They still had a couple of feeder breakers trip on the below 57.5 during this event as well. They have adjusted that finally to provide that, you know, multi-cycle window. I think they put in like a 10-cycle window. So hopefully we won't see any more feeder breakers tripping. And as far as the overvoltage, there are a couple of things that they're working on. They are increasing the fast overvoltage protection to 1.4 per unit. So previously the OEM said they could not extend this. Now they're saying they can. So this is being jumped up from 1.25 to 1.4, but they will not be able to inject current above 1.25. So they will go into momentary cessation once that voltage goes above 1.25, but they won't trip unless it gets to 1.4. They're also reducing the K factor to reduce the reactive injection. So I just want to point out for all of the OEM 1 inverters, they have the overvoltage situation, they have the overcurrent, they have the volt phase jump. For all of these facilities, we are recommending that they fix all of these mitigation plans at their facility simultaneously. And that's being done at these 6 facilities. Once that's done, we're going to reach out to other facilities with these inverters to recommend they start implementing these corrective actions as well to preventively to prevent any potential events with the other units tripping off as well. So this is what happens is you have a voltage disturbance on the grid side, and then you have unbalance on the phases, and then the DC side regulation cannot recover quickly enough, cannot regulate quickly enough. So you have unbalance on the DC side by either over 100 volts or 200 volts, major versus minor. And that tripped off all the inverters at two different facilities here. This is something that had been seen in previous events, not in events at ERCOT, but I believe in California. So the OEM was already working on a fix for this. They already had a software update in testing at the time of this event. It has finished testing, and it would improve the DC regulation response time, basically speed that up to improve the ride-through capabilities to not trip off these inverters. So of these two plants, one plant has already implemented the software upgrade, and the second is scheduled to have this implemented in November. Back to we're calling this a slow ramp after a low voltage ride through. So this is a single plant, an older plant. Last year it tripped on the feeder breaker over voltage. They disabled that, but this is a plant we have been working with throughout the past year. They were in the process of increasing some settings. A couple of things. They had an LVRT mode that was designed to take active current all the way to zero to provide 100% reactive. They were switching that mode to reduce megawatt only as much as they have to, proportional voltage, and enough to provide that reactive, but not all the way to zero. They were also increasing their fast overvoltage protection trip to 1.35 per unit with a 5-second delay, which is a vast improvement of what it was before, because they had originally set at 1.2 with 0 delay. Through back and forth with this, we were trying to figure out why they had this slow ramp rate after LVRT, as you can see in that top right graph. And they found out that they actually had LVRT disabled during this event. That's why they had this slow response after voltage recovered. You had some PPC and inverter interactions that made this weird ramp rate and then this odd step function you see as well. So they have now enabled the LVRT, so they're expecting, for one thing, the megawatt would not drop nearly as much as it did in this event, and then it would come back immediately upon fault clearing. So all of this has been implemented at the site. They are doing some PSCAD modeling to reflect these changes, and we'll resubmit those. They're also looking into these oscillations that they saw during this event as well. All right, back to the plant with the momentary cessation. This is its response. As you can see, it did not respond immediately after the momentary cessation ended and the voltage recovered like we were expecting. It still took them 1.5 minutes or so to come back up, even with the new power plant logic. So again, this is a legacy inverters, an older plant. And what they found out, it was actually a loss of auxiliary power that occurs when there's a large phase jump. They actually did have momentary cessation and disabled during this event, but the loss of auxiliary power caused these inverters to trip. It's very difficult to determine from their logging capabilities if it was due to voltage magnitude below 0.9 or if it was a phase jump. So the only potential corrective action, was to potentially install uninterruptible power supply at each inverter. But even the OEM was not certain that this would fix the problem, especially for an event with a large phase jump like the Odessa events. So we're still working with this plant. It doesn't look like they're going to be able to meet our VRT requirements, our requirements to provide reactive. So this is going to be an ongoing issue. This is the plant that we're really going to have a hard time getting up to speed to meet our requirements. Next, we have a grid over frequency, but this was actually we think this was probably a wrong fault code because the conditions for the overfrequency of 60.6 hertz for 600 milliseconds was not met. And the generator owner realized that. So they found out it was likely some kind of fault code registry mapping that was incorrect. So the actual root cause of this inverter tripping is unknown. Again, this is the OEM3 that's out of business. So we have been working with the company that took over those service contracts. They did go through with the GO and the OEM to really work on the FRT and VRT settings to reflect the actual equipment tolerances instead of just having them loosely based on the PRC 24 or nodal operating guide requirements. So they have extended these out pretty significantly. There's actually 2 of these plants that have done this work. They've set all of their frequency settings now have a 5-second measurement window because there really is no technical reason for inverter protection that these things need to be tripping off for a frequency, especially anywhere near what our requirements are for conventional generation. So they've extended those out. They've also extended out their voltage ride-through settings as well. And they have fixed the logging issues. So hopefully we won't be seeing any more issues with this facility as well. Again, kind of the same thing with one on the bottom, another plant with the OEM3 inverters, kind of had 47 megawatt loss, weren't really able to identify the root cause. They had their inverter fault codes overwritten by the PPC. So they've kind of gone through the same process, extending out the FRT and VRT requirements. And, they've done some work to improve their logging capabilities so they're not overriding these fault codes. And then finally, we had one more plant that lost about 5% of their inverters, 5% of their megawatt. Out of the 80 to 100 inverters they have, about 5 of those tripped. Two were due to a high internal temperature, and 3 were to overcurrent. And they were also unable to identify corrective actions. They are having issues with their SD cards recording the fault codes got overwritten as well. So they were doing some work there as well. So just to wrap it up, so in a summary, we've really gotten a lot further since the 2022 event and implementing corrective actions than we did in 2021. The knowledge we gained from the first event, looking at these root cause analysis, even with the new ones, getting the relationships with the OEMs, we were really able to get things in action much quicker this time. But we do have several other activities that we're working on right now. We are in the process of drafting new nodal operating guides for our voltage and frequency ride-through requirements for inverter-based resources, and we're basing those off the IEEE 2800 standard that just came out. We are meeting with several OEMs of both wind and solar to determine what proportion of the current fleet can meet these new requirements. We've had a couple already. We've got another 5 or 6 that we're going to meet with to see, what can meet these newer requirements and where we need to, what we need to adjust a little bit. We're going to continue to follow up with the facilities involved in both events to make sure these corrective actions are implemented. It's looking like all of this will be implemented by the end of the year. A lot of it's been done already, but we're really staying in close communication with these facilities, make sure these things are happening. We're also going to reach out to all the facilities with the same inverters involved in these events to recommend these same actions, volt phase jump, extending the threshold, or disabling, extending voltage and frequency ride through, things of this nature. So we're going to do a lot of outreach next year to the rest of these facilities not involved in these events. We're also analyzing smaller events similar to Odessa, which include both a system fault and a loss in IBR output to identify and mitigate these abnormal performance during these events. So we have new tools that we're looking at to using the PMU data, real-time PMU data, looking at our ACE to see, hey, there was a system here, we had a loss of solar of more than 100 megawatts. We see a fault occur at the same time. Let's send out an RFI, or let's reach out to this facility to see why they tripped, to see if that fault was close by at their facilities, to see if they're really performing the way they should be. The last part is really looking at the models. So we are validating the models of all these affected facilities compared to the PMU data and the digital fault recorder or relay data that we have. Anything that's not matching, we're requiring these GOs to go look at these models and make sure they're actually reflecting their actual resource performance. And then also any of these that are implementing these corrective actions, we're expecting them and requiring them to make these changes in their models and resubmit those dynamic models as well. And I believe that is it. So I think it's time for
Okay, Patrick,
questions.
thank you. You compressed an awful lot of information into a very short period of time. So let me begin with the first question. Do you have any system disturbances planned in the near future to check up on how the remediation is going?
That's a great question. I mean, I'm thinking about going out to Odessa with maybe some large pieces of conduit and just throwing over the fence to see some sparks and then come back and check the systems. I don't know. Yeah, that's the
That would,
tricky part about this, right? We're doing all these things and
uh,
we really don't, we're hoping it's gonna fix it, but we don't know. So we're working on our tools to, when we have disturbances that have faults, we know when there's a fault in the system, so we can go look and see, hey, did we lose any IBRs for this event?
yes,
So it's really having to do that.
that's a really meticulous process you have to go through to check it all out.
Yeah, I mean, it's really problematic when you don't know until there's an event.
Okay, I'm going to move to the Slido questions. There's one here that I know I was dying to ask during the presentation. I know you can't answer it, but we'll ask it anyway, just out of respect for the people that submitted it. It would be really helpful to some of us that you could share the names of the OEMs.
Yep, I'm sure.
Yeah,
I'm sorry.
it would be helpful, yes.
Yeah. Well,
Okay,
we
next
got
question.
the OEM. We need the OEMs to agree to that.
Yeah,
I've been
yeah.
working on them, but they haven't, and my legal department has told me not to. So I am.
Right, I know. So, question from Jason Kemper here. Were any of these causes of reduction not directly related to the specific OEM, but rather to plant design or a third-party controller's design?
Oh yeah, definitely. Specifically, feeder breakers tripping off. That's got nothing to do with an OEM. That's poor design. That's someone designing the breaker to trip immediately directly on the voltage ride-through curve. Um, plant, plant level controller interactions as well. That's really not from the OEM side as well. Um, there were a couple others, I think, but those are the two ones, the main ones that stand out. But I would say most of them are from inverter level um, protective functions that were tripping off.
Yeah, okay. Question from the on the thermal side. Not sure if you've been involved with this, but what corrective action was taken to prevent the original fault at the gas power plant?
I'd have to go back and look at that. I think
Yeah,
yeah, I mean, they've replaced the lightning arrestor. Um, they told us corrective actions, but that's not something I've been really
right.
focused on. So I
Yeah.
have that answer, just not in front of me.
Okay, next question. Were the PV plants directly connected to transmission voltage or distribution voltage or some of each?
This is all transmission.
All transmission. Okay. Has ERCOT increased frequency response reserves to cover a possible larger total system megawatt trip risk?
Um, Specifically from these events, no. We do have plenty of frequency response reserves, though. Um, I'm not too involved with that side, but anything particularly increased because of these events, no. But we did have some react. We did have the responsive reserves, like the load resources that allowed frequency to recover quite quickly for the second event. And we do have, a lot of frequency response that occurred during these events as well. But as far as an increase just from these events, I don't think so.
As I recall, the loss of the two nuclear plants was the single largest contingency in ERCOT.
Yeah. Hmm.
Yeah. still the case. Okay. Does ERCOT plan to do more PSCAD modeling before commissioning to identify some of these issues before they occur?
That's the plan. I mean, we would like to.
Modeling.
The resources is a major concern with this. So testing the EMT models from each of these plants, it's something we're trying to do, attempting to do, but we are resource limited for this.
Yeah, it sounded from what you said too, like there was some question associated with the accuracy of the models that have been provided. Still need some.
Yeah,
guess
and that's
improvement.
kind of we have to assume the models they're giving us are correct. I mean, the
Right.
only way we're going to know if they're not correct if there's a system event like there was, and we say, oh, well, your model did not, your performance, your response was not the same as your model. So those are the ones we're saying, hey, obviously your model is not correct. So we are asking those entities to go back and tune those models to make sure they're correct. And then after they're tuned that models, if they've done any corrective actions, they need to go back and put those corrective actions in the model and resubmit as well. So we have a lot of modeling work left to do from this
I
event.
think everybody does. It's a bone of contention for everyone. Are the GOs fixing or addressing root causes voluntarily based on ERCOT's recommendations, or is ERCOT enforcing mitigation and corrective actions based on the LGIAs, et cetera?
So what we did after 2022 event, we do have some language in our nodal operating guides that state if you do not meet your performance requirements for voltage ride-through, you are required to submit a mitigation plan and timeline to ERCOT and the TOs. So we relied pretty heavily on that language in our guides. So we required all these facilities to submit a mitigation plan and a timeline in writing to us, and we're following up with them, to the due date to make sure that they're getting these things implemented. We gave them a couple of weeks to submit these plans, and then most of this should be put in place by December. We have not done any enforcing of this, but it's definitely on the table if anything doesn't get done by the end of this year.
Okay, the next question. Has ERCOT considered opening the circuit breakers to the plant until such time as the remedial actions have been taken? No, that's just.
We've considered it. That had gone further than that.
The ultimate
we're
control.
dealing with the summer. We're dealing with tight generation. So taking generation off our system is not something we really want to do. We'll do it if we have to.
Sure.
And it has been discussed that if these plants do not get these things fixed, then it is a course of action that ERCOT can take if it comes down to it.
So a question from Christian Schaefer. Christian is one of our colleagues in Australia. Is there a minimum SCR requirement for IBRs in the ERCOT network? And has your consideration of this changed in light of the events?
Not that I'm aware of. I'm not aware of a minimum SCR requirement. This is a weak area out in West Texas, and we're aware of this, and this is likely why we're seeing the events out there. Well, not to mention that's where all the solar is, but I'm not aware of any minimum SCR requirement and for our connection.
Okay, another question here. Is the distribution of OEMs approximately uniform across the state, or is there a higher concentration of certain OEMs in this geographic area?
I haven't really looked at that. Most of our solar is going to be out in West Texas, so I haven't looked to see if there's other OEMs that are more, dominant in other areas of the system. I'd have to go in and look at that.
Yeah. So, question from Albiston. Can you give recommendations for TSOs where most of the power of IBRs is from the distribution and protection settings are not well regulated for IBRs? you're focused on the transmission system.
Yeah, I haven't really looked at any distribution.
Yeah, I would just say as some consideration is that IEEE 1547, which, what was it, 2018, I think, when the last version was done, deals with that question in large part. So Anonymous, can we get the presentation slides? Yes, they'll be posted after the, probably within a day or two. Another question from Alp Alveston. Has any legal action been taken regarding power plants that were unexpectedly out of service?
No.
No. Gustavo Brunello, a comment. Inverter manufacturers shall be asked to implement fault and disturbance recording within the inverters. If that's a change that's coming up, or exactly what that refers to.
We do request some of this inverter level data. We did get some. I don't think we have specific requirements for inverter level data, but yeah, it's something we probably need to look at. We do have requirements for PMU data and like DFR data and things like that at substation, but I don't think we have requirements on inverter level data.
Okay. This next question I think you addressed, but maybe just to clarify it, was it mainly the inverters that tripped, or did reclosers or breakers trip?
Both. I mean, we did see some breakers. We saw some feeder breakers, mostly due to, well, we saw over voltage and frequency, but most of it was inverter tripping.
Question about IEEE 2800. Do you think that its implementation will prevent some of these issues in the future?
Yes, I do. Unfortunately, it's going to be difficult to go back and apply some of this stuff to our existing fleet. I think it will definitely help for, newer projects once we get this implemented. We are making the attempt to not allow any grandfathering in with these new requirements. That's why we're going through the process with the OEMs to get an idea of what proportion of their fleet can meet these requirements. Some of them are saying it shouldn't be a problem. Some are saying it's difficult to tell. So we're in the process of putting a lot of this data together right now. But it should.
Yeah. Next question is related. Do you think there are issues that should be addressed in an update of IEEE 2800, like how frequency is measured?
I think it is addressed. I haven't read through 2800 completely, but I mean, as far as the measuring frequency, as far as like that number of cycles you need, I think NERC has addressed this pretty well in their event reports. They will address it again in this event report. I thought that there's a pretty extensive section in measuring frequency in IEEE 2800. I may be mistaken, but if it's not in there, it definitely should be in there.
Yeah, it'll probably be a few years before an update is done, but we'll also be having a NERC presentation next month. Ryan Quint will be giving us an update from NERC on this broader topic as well. Does ERCOT have a real-time tool to monitor IBR loss, or does ERCOT manually check IBR generation loss once a fault occurs in a nearby area?
We've been working on this. We did get a Pi upgrade recently that should allow for event notifications. We need to get that up and running. That's on my to-do list. But right now we've been manually checking. We have, a tool that we have to manually go in and say, hey, were there any solar events this week? And then if we do see an event, I'll go and look at our PMU to see if there's a fault. But we are working to improve those tools. We are working to improve the PMU application to really be able to pick out these types of fault events we're looking for to notify us for those as well. So right now it's more of a manual process, but we're working on automating it.
Okay. I'm going to take one last question, Patrick, that's been trying to get up to the top of the list for a while from Chuck Ladd. Is it necessary to trip the feeders at all during frequency events?
I don't think so. I haven't heard anyone tell me or give me a reason why they need to. I mean, even the inverters, I'm not sure why some of them, a couple of the facilities have kind of taken the hint to say, why are we setting this frequency, the trip at frequency below 57.5 immediately? And they've just gone in and they said, all right, we're not tripping on frequency anywhere between 57 and 63 hertz. And even at that, it's got to be outside of that range for 3 seconds. It's like, hey, there you go. I mean, if you're not protecting equipment, if you don't need to trip on frequency, don't trip on frequency. But it's been difficult because people see these requirements and they can't get around that they don't have to set something around this level.
Okay.
So that's
Problem
something,
solved.
again, as the industry as a whole needs to kind of understand the intentions of these requirements.
Yeah. Okay, so we're just a little bit past the top of the hour. Going to need to wrap it up. Patrick, I want to thank you for this really fascinating webinar and for the great insights into the challenges and opportunities associated with the inverter-based resources. And as I mentioned earlier, an email will go out once the video file has been posted, and we'll answer the questions we didn't get to and get them posted as quickly as possible. We really appreciate your engagement and look forward to seeing you again soon. We have a webinar coming up on November 15th on the Irish journey to very high shares of IBR generation in an electrical island like ERCOT, and 2 more webinars each month until the spring workshop in March, one of which in December I mentioned will be with Ryan Quint from NERC, and a little broader look at this particular issue. And you can find further information on all of our webinars and meetings on the website at esig.energy under events and in the newsletters and informational emails, and you're all invited to attend. Patrick, thank you once again for this very timely and informative webinar, and thank all of you for your interest. We look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe, and thanks for your participation. See you soon.